All right, let's get right into it. We're surrounded by automation, right? From the phone in your hand to the power grid that keeps our lights on. But have you ever really stopped to think about how all these automated systems actually see the world around them? I mean, how does a system know if a tank is full, or a reactor is getting too hot, or if the water coming out of your tap is actually clean? Well, today we're pulling back the curtain on the unseen senses of industry, the sensors that measure our physical world.
So, back in the day, it was all about human senses. You'd have an operator, just like this person on the left, literally using their eyes to check a water level and their hands to crank a valve. And hey, it worked, but it needed someone there, watching all the time. Now on the right, that's the modern way. The person is gone, replaced by an electronic system. But for that system to do its job, it needs a way to see that water level. It needs an eye.
And that's where this word comes in, sensor. The most important thing to get here is that a sensor is basically a translator. It's a bridge. It takes a real-world physical thing like temperature or pressure or level, and it converts it into a signal that a computer or a controller can actually understand. It's the device that does the seeing, or the feeling, and turns it into a language of electricity and data. So, let's start with one of the most basic, most fundamental measurements in pretty much any industrial process: temperature. Getting the temperature just right is absolutely critical for everything from making chemicals safely to pasteurizing your food. So the question is, how do you give a factory a sense of touch?
Well, it turns out there are three main families of these electronic thermometers, and each one kind of has its own superpower. You've got the RTD, which is the super reliable and stable one. Then there's the thermistor, that's the incredibly sensitive one. And finally, the thermocouple, which is the tough one that can handle some seriously extreme temperatures. Let's break them down.
First up, the RTD, or Resistance Temperature Detector. The idea here is actually pretty simple. When you heat up a piece of metal, its electrical resistance goes up in a very predictable way. So if you can measure that resistance very, very precisely, you know the exact temperature. RTDs, especially the ones made of platinum, are the workhorses. You use them when you need accuracy you can count on day in and day out.
Okay, so if the RTD is a steady workhorse, the thermistor is like a thoroughbred racehorse. Instead of a metal, it uses a semiconductor material. And this is where things get really different. As the temperature goes up, its resistance goes way down, and I mean dramatically. Just look at that curve. A tiny, tiny change in temperature causes a massive swing in its resistance.
How massive are we talking? Well, a pretty standard thermistor can change its resistance by a staggering 1,000 ohms for just a single degree Celsius change in temperature. That unbelievable sensitivity is why they're perfect for detecting even the slightest little temperature shifts with absolute precision.
Now this is where the physics just gets plain cool. See, unlike RTDs and thermistors that just change their resistance, a thermocouple actually generates its own electricity. It's called the Seebeck effect. When you fuse two different kinds of metal wires together and you heat one end, the electrons literally start to move, creating a tiny but measurable voltage. You're turning heat directly into an electrical signal. It's amazing. And by picking different combinations of metals, say iron and constant tan for a type J or platinum and rhodium for a type S, engineers can build thermocouples for all sorts of different jobs. What's so great about this graph is you can see the engineering trade-offs right there. The type J and K have a really steep slope, which means they're very sensitive. But look at the type S. It's less sensitive, but my gosh, look at its range. It can handle incredibly high temperatures, perfect for things like furnaces or kilns. All right, so we've taken the temperature. Now let's tackle another super fundamental question in any factory. Is this tank full or empty? And how full is it exactly? Knowing the level of stuff, whether it's liquids or solids, inside tanks and silos is just absolutely essential.
So before we even get into the cool gadgets, you gotta understand the basic questions an engineer has to ask. First, are you just trying to see if the level has hit a specific point, like for a high-level alarm, or do you need a continuous measurement of the exact level at all times? And second, can your sensor actually touch the material, or does it have to be non-contacting? The answers to those questions will tell you exactly which technology you need to use. Let's start with the absolute simplest concept, one you've probably got in your own house right now, the float. It's exactly what it sounds like. A float sits on top of the liquid. As the level rises, the float goes up with it, and a little magnet inside trips a switch. Boom! It's a classic example of a simple, super reliable contacting point level sensor.
But what about solids, right? Like grain in a giant silo?
You can't really use a float for that, so instead you use something like this, a rotating paddle. A little motor just keeps this paddle spinning and spinning until the grain level rises up and covers it. The material stops it from turning, and that resistance flips a switch. Another really clever, simple mechanical solution.
Now, let's jump into the high-tech, non-contact world. An ultrasonic sensor basically works like a bat's sonar. You mount it at the very top of a tank, and it sends out a little pulse of high-frequency sound, a chirp. That pulse travels down, bounces off the surface of the material, and echoes back up. The sensor's brain just measures how long that round trip took, and since we know the speed of sound, it can calculate the distance down to the surface with amazing accuracy.
So, okay, we can measure temperature. We can measure level, we know how hot something is, and we know how much of it we have. But what if you need to know more? What if the quality or the actual composition of the stuff is what really matters?
And that leads us to our final category, which is maybe the most advanced of all, analytical sensors. These are the sensors that can actually peer inside a process and measure its chemical or physical properties in real time.
Let's start with a property called turbidity. Now that's just a fancy scientific word for the cloudiness of a liquid. It's caused by tiny little particles that are suspended in it, and measuring this is super important for things like making sure our drinking water is pure or that a beer is perfectly clear.
So how do you measure cloudiness with a sensor? The idea is actually brilliantly simple. You shine a beam of light through a sample of the liquid, and you stick a light detector off to the side, at an angle. Now, if the water is perfectly clear, that beam of light just shoots straight through, and the detector sees nothing. But if there are particles in there, they scatter the light in all directions, and the detector picks it up. The more scattered light it sees, the higher the turbidity.
And the analysis can get even more sophisticated. The really key insight here is that how that light scatters actually tells a story. You see, different sizes and shapes of particles create totally different scattering patterns. By analyzing those patterns, a sensor can learn not just that there are particles, but it can even get clues about what those particles might be.
Okay, here's one I know you've seen before, the pH scale. It's that fundamental measurement of how acidic or alkaline a solution is. And believe me, from making pharmaceuticals to growing food to treating wastewater, controlling the pH is one of the most common and critical jobs out there for an analytical sensor.
So how does a pH sensor even work? Well, this schematic here shows you just how incredibly complex these things really are. It's not a simple measurement at all. A pH probe is an ultra-precise electrochemical cell. It uses a very special kind of glass that develops a tiny little voltage across it, and that voltage is directly proportional to the amount of hydrogen ions in the liquid. So at its heart, it's basically a highly specialized voltmeter that's designed to measure the electrical potential of acidity itself. So we've seen all of these amazing technologies, sensors for temperature, level, chemical composition. But in the real world, with hundreds of different options out there, how does an engineer actually pick the right one for the job?
Well, it really comes down to a big balancing act. First and foremost, you gotta ask, can it survive? A sensor is totally useless if the heat or the chemicals in the process just destroy it. Then you think about accuracy. Is it precise enough? You have to think about the material itself. Is it sticky? Is it corrosive? Is it gonna coat the sensor and mess up the reading? And then you have the practical stuff, like how hard it is to install and how often you're gonna have to pull it out to clean and recalibrate it. It's a real engineering puzzle.
You know, from a simple little float switch to a complex pH electrode, these sensors are what allow our automated world to perceive, to understand, and to control itself. They are the invisible, tireless senses working all around us every single day. And it kind of leaves you with a really fascinating question. As our technology gets more and more advanced, what new, unseen things are we going to need to measure next?